Maybe second time's a charm. Hey, second time's a charm. Okay. So last time we were out at the brick and we went through ultrasound, and you guys got to take your own measurements and that. I did get, they offloaded them and sent them to me late last night, but I didn't see them. So I'll upload them when I get home tonight. So you'll have copies of those images that you can use. When you look on the ultrasound homework, you'll see you're supposed to upload the image and then you're supposed to give a count of the objects. That's the next question down. You know, it would, if you bothered to take a picture of it, as mentioned, it'd be kind of cool to put that in there, you know, and include, so you can kind of see, was your guess reasonable on what that was. Realize when you're taking a cut plane through there, some of them will be brighter or less bright because you're going to hit some of them straight on. They'll be in the actual beam. Some of them will be right on the edge of the beam, so it won't be as strong. But that's actually kind of a helpful thing. You don't know whether it's in or out, but it does give you some idea of difference off. So now we're going to move to our last regular topic. Right? So if you notice, the end of the semester, I told you, is our project, and our project's going to center around an optical tomography project that we'll do. But this will be our last of our regular topics covered in the book. Right? So MRIs is also, you know, the amongst the regular medical imaging, it's the most recent one that's been developed. It's got a lot of really cool advantages. Part of this is actually due to the fact that a lot of the concepts and ideas are fairly more recent in their development. You'll notice, for instance, we'll talk probably more next time when we get into the technology, although you'll still see the name of an RF pulse here. You know, and that's, it's not that we're actually doing the radio frequency in the sense we're doing through an RF coil, and one of the two inventors of NMR, discoverers, whatever you want to call it, actually originally worked through the World War II on developing radar at MIT for the war effort in World War II. And as a result of that, he was able to see the absorption of EM spectra into bulk materials as a byproduct of RF work. And so that actually laid the groundwork for NMR. So it's, all this has been the ideas post-World War II, really didn't, you know, MRIs is like a regular imaging technique, didn't come into sway until the 80s. So it is, of our imaging techniques, by far the more recent one that's going on. And it's going to have some really nice properties for us. Most importantly, well, let me ask you, actually, you guys, because a bunch of you have had radar-related stuff, I know from your projects, and all of you should have had some amount of, you know, electromagnetic fields, both through physics and also taking your basic course doing Faraday's equations and whatnot. You know, Faraday's induction is actually used in our current stuff. We'll mention it as a side area. It is in the book too. So a lot of this carries in. Let me ask you the question. What do you think MRI, what's the main operating principle behind it?
Resonance.
Okay.
Resonance of subatomic particles.
Okay, and what's that? Right? You can resonate in lots of ways. Right? So what's the thing that's resonating?
Electrons.
Nope, it's not electrons.
Hydrogens.
So it does have to do with hydrogen. Particularly it has to do with the nucleus. Right? Now electrons can resonate on these, right? They've got a fractional spin, right? So our big concern is going to have to do with, you know, let me skip one, I'll come back here. Our big concern is going to have to do with some particle, and it's got to have some spin for us, yeah.
So like water.
So yeah, if the hydrogens are attached to water, this is why it's such a good one to us to use, right? It's all based on, remember your standard model of physics? I presume everybody's at least heard of them, right? We have two big categories of things, fermions and bosons, depending on what type of statistics within physics it operates under. Fermions have fractional spins, right? And so proton is a fermion, right? You know, in particular because it's made up of an odd number of quarks, and quarks are fermions. Do you think neutrons, do they have spin?
Well, so the book said that you could have spin if either you have an odd number of protons or an odd mass number. So that kind of implies that neutrons.
They do, because they're made up of an odd number of quarks, right? So, you know, protons versus neutrons, it's 2 up, 1 down, or 2 down, 1 up. But no matter which way you go, you do get that, you know, half spin property going off it. So, yeah, they are composite fermions. They follow Fermi-Dirac statistics. So neutrons can do it as well. So that's why straight hydrogen is good, but deuterium, no. Right? I go to tritium again, okay, it appears again. You know, so there is a spin that's associated. When you have aggregate ones, right, you'll get an effect, right? The more of them you've got built up in the nucleus will depend on how much of a spin constant to it. That's why protons have a really strong one. You can see like it's significantly stronger than others that are out there. Right? So it's a very nice one to be able to image, but that doesn't mean there aren't other ones that are worth imaging as well. Right? Now, it still hasn't gotten to the idea of what the heck am I using to image this? It's resonating, which suggests a spin, right? And in particular, we're going to have, right, we're much more concerned with the protons than the neutrons because of something. Neutrons are not a good imager for us, right? Even though they do have this quantized spin situation. Anybody got an idea why? Magnetic field. Right, that is the whole thing. Because it is a spinning charge, there is an induced magnetic field caused by this spinning charge. That's what we're going to make resonate. So we're going to have an outer magnetic field and an inner. We're going to actually have a bunch of different magnetic fields. So this is where it gets really important to keep your magnetic field straight. There's going to be an external imposed magnetic field we're going to call B. Right? There's going to be an internal field kind of caused by the matter itself in response to all this, which we're going to call M. Right? And then when you get to the coils, there'll be a conversion of that magnetic field caused by the ones in the body into what causes flowing charges within the coils. And we're going to call that B capital R, or B superscript R, right? A response B field. These are different fields. Please do not think they are the same. You're just trying to use magnetic field letters without being too horribly confusing. Okay, so that's kind of the big issue that's going on with those. So we're going to have magnetic field. So this is yin and yang, right? Since we're doing magnetic field caused by charges E, so we've got a whole EM thing going on. And this gets us to that kind of important area of moving charges in a field and being able to induce things from this. And this is where the correlation to RF and everything else drops in. Now, why do we want to do this? Right? Take a look for a second at these images. Without even concerned too much of what they are, look at the quality of the image and the detail you're able to get and compare it to anything we've done so far. Right? That's pretty crazy, isn't it, if you think about what's in here. So amongst features on here, number one, you get a crazy type of resolution. And the resolution in particular, MRI is really good at distinguishing tissue types. Now, X-ray was really good for distinguishing hard versus soft. MRI is really good in between all the softs. Okay? It still will do a good thing of different types of bones, but if you notice the bone, it's getting pretty close to saturated. So it's not as good on bone, but that's okay. Most of the things we're trying to image are going to be more soft. Now, you will still see between different bone types, you'll still get stuff, right? So that's not to say it's not good. It's just the comparison between X-rays and MRI is very strong in quality difference in soft tissue. It's, nowhere near as big when you get to more dense tissue structures that are on. But if you look at, the brain or the liver in here, you can tell a crazy amount of detail with it. All right? How about damage to tissue?
You mean like from the actual?
Yeah, I mean, anytime you do any imaging, you cause damage. I don't care what anybody says, right? But it's relative. So, if you were to look at, for instance, CT versus PET, they're both fairly damaging that goes on, right? And a lot of radiation that's imposed on these, right? Versus ultrasound. Can ultrasound cause damage? Absolutely it can. You can't. Does it at the levels we use it at, does it cause damage? No, we ramp it down low enough and it really can't cause any damage. You have to ramp it up really high and then you can cause heating moderately that can be damaging. And we can have some of the resonance in that one that can cause things to shatter. Potential for stuff, but we just keep it low and that's why we have more grainy images because it ain't worth pumping that much energy to make it clean. You can tell what you need to do. There are ways you can make ultrasound look even cleaner too, but overall the difference between it and MRI, who's winning? MRI for the most part, right? So MRI seems to have some pretty good stuff going on. Does MRI have damage to tissue?
Yes, but not very much.
Yes, but not very exactly so. Right? Think about it, because what's going on? It's inducing primarily a magnetic field. Do you go through magnetic fields all the time? Do magnetic fields strongly interact in a dangerous way with you as a person? No. Right? Can they interact with you negatively? Yes. Right? But it's much more difficult to cause damage from this. Much, much more difficult, right? So, and the amount of damage you're going to cause is low. So I get a crazy good resolution on tissue types. Really, the chance for damage is like ultrasound down on the floorboards, right? Pretty much that most people call it non-damaging. And for the most part, that's a pretty safe statement, but you should never think there is a complete immunity to it. These are great things, right? You should always be suspicious when there's great stuff, right? So what's the disadvantage? Because it's got to be there, right? It is expensive, right? Why is it expensive? It's just magnetic fields.
Really uniform in order to get a good image.
Okay, so we have to put a lot of precision magnets along this. We're going to add, in addition to basic magnets, we're going to have to add shim magnets every day. You're going to have to tune it to get everything precise so you have a good field. All right? Anything else?
Freaks patients out.
It does. It is, right? It's a tube, so it's a little bit dangerous to people. And part of that effect too, right? If it was really quick, you wouldn't worry about it, wouldn't freak you out. But in addition to putting you inside some tube that scares people claustrophobia-wise, what else does it do?
Just loud.
It's loud and it's long.
And you can't have any metal in there.
Yes. Yeah. Which includes certain types of things that might have injured you. Right? So if somebody has, like, if you've got somebody who is injured on a battlefield or something, they might have shrapnel. You got to ask the question: is that shrapnel magnetic? Otherwise, that changing magnetic field is going to turn that shrapnel into an egg beater and stuff.
Oh my goodness.
It's I mean, I don't mean to sound gross on it. It's a realistic issue. You've got to be very careful about potential damage from those kind of things. I mean, when it first came out, you had to be very careful with types of implants and other types of things. We're just lucky that gold, for instance, is, not a ferromagnetic, for, teeth and other types of work. Because even when you have porcelain ones, there's usually gold on the inside. I don't know why. There's just a general engineering. Whenever you see anything and something happens, particularly when it's an expensive thing, as an engineer, you are duty bound to understand why the heck they chose the expensive thing. It's actually for two properties, right? One is it's very corrosion resistant. You ever see gold with tarnish on it? Yeah. So think how caustic your mouth is, right? You got a lot of stuff that dissolve things. Second one is soft. And that might seem a weird thing as a good property you want, but you want sealing when the dentist, pops on whatever he's popping on, crown or whatever. And the gold, when they apply pressure to it, will bend and fill in any gaps. So it prevents junk from coming back into the sealed area. Right? So gold is always going to be used in the mouth. But luckily it doesn't interact with us. So that's good. Right? There are certain types of screws that can interact with you. Right? Titanium, generally safe. So this is a preferred one, but there are some ones that, early on particularly had other things. So that's when we consider implants into the body, we not only have to look at the other properties, since there's a high likelihood doctors will want to do an MRI, we got to make sure that that's also something that's going to be safe inside the MRI unit. Is there anything that's not safe inside an MRI unit that we have to do as implants and stuff? Other ones we generally watch out for. Pacemakers, right, because you'll have a lot of stuff in electronics. Now there is a design, there's one of the reasons why we want to always design new products and other things. If we can reduce that, we make it safer to do. Right? All right, so that's a big one. There are some implant types that also do. You'll see some will get stainless steel hips and things of that sort that can create issues. Anyway, so there are some potential dangers depending on the type of things you have added to your body. Is there anything else potentially we have to worry about with MRIs? Cost, scariness, loud noises, potential interaction with certain implants, other things that are in there. So it has kind of an interesting side thing. It is expensive. It will have a power bill that's associated with it. So it's also going to have another one. We need a very good measurement with low noise. Very good, right? In order to get a really good measurement on those coils that's very low noise, you generally have to use like liquid nitrogen to cool it. And by super cooling them, then we can get, these are going to be very small pulses we're receiving. We can't have noise, so we have to lower the temperature. So it's expensive in that we also have to do these kind of crazy super coolings to them. And all of this requires a group of highly specialized people to maintain and whatever else. Hence why the cost builds up. And the more we don't use it and we use it for specialized purposes, that means the less insurance wants to pay it, which means the less you're doing it over a large number. So there's also an economics factor that comes in. The negative side of that is the more they don't pay, the more expensive they have to pay on the other side. So to me, it's kind of a sad statement. There have been a few attempts to make MRI more common, which would affect some of these cost areas, including making small, lower ones. The one you're going to test was originally designed, or do you test on, it's over in physics, was designed actually for doctor's offices for checking, doing a quick MRI of a foot or a hand or things like that. It's a very common one. Somebody gets an injury doctors would like. It was designed as a low-cost, easy-to-operate one, and it did that nicely. Cheap, a doctor's office, your standard general practitioner could afford to have one of these things and run it so that anybody who says they've got an injury, you don't have to take an x-ray of it. You can do the proper thing and take an MRI of it. You could do it right there. And it was fairly easy to maintain and stuff like that. A lot of good advantage, right? Thing shot it in the rear, insurance didn't want to pay for it. Even though it was cheaper, they just didn't want a general practice of paying for MRIs, which shot in the rear getting cheap MRIs, which would have reduced their costs. This is one of those cases where, as an engineer, you can look at something and you can actually notice every advantage is on the side of it, but your product can still get shot down, right? You know, and this is as stupid as a stupid test on it. But you do have to think about economics, unfortunately, sorry, in building stuff, and that's one of the weird ones. I still don't understand why it doesn't work. When you test the machine, imagine that was in every doctor's office and you could get an MRI image for fairly cheap prices, you know. So a kid busts their ankle or something, they can look at it and see was there really a tear or not in minutes. Craziness. Anyway, you can see the contrast of these. It's awesome between the tissues here. You can see white matter versus gray matter inside the folds of the brain, right? That's an incredible benefit of it. Like I said, the liver tissue, you can take a look at the lumbar spine area of it, and in addition, you can see the spinal cord and blood flow and everything else running through it. You know, you can take a look, you know, that one is a fracture in the wrist. Notice it's not as easy to see it in the bones, but you can see the damage between them, so it does kind of show up a bit. So it is still useful, and you can see without the bones overlapping, they really come out in 3D. They are separate, so you're not trying to unresolve them. They never smear. Really, when you're going to take the measurement of this, we're going to just sample. It's going to be called K-space, but it's basically Fourier space. You do an inverse Fourier transform. Technically, it's 3D, but it's, you know, boom, there's your 3D image. It's just, it's as nice as you could get on it. So in that sense, that's why a lot of the clarity is in there. You know, you can see a stroke readily. You know, take a look at the area of the brain where it's been damaged by the blood flow that goes into there. Pops out nicely. You know, you can see with multiple sclerosis, you can see effects in areas of the brain. You can see more recently, people have done tests on this and discovered, for instance, most of the Alzheimer's patients, you know, particularly get affected in this area of the brain. And you can watch on MRIs of them. You can see those type of activities. You can do functional versions of these. The book doesn't really talk about them, but I'll mention a little bit because I think it's functional MRIs are an important idea that comes in. But you can kind of think of those as looking at dynamic flows rather than static tissues. Regular MRI, static tissues are the main goal. When you go to functional ones, you're taking a look at how things are changing inside, so the ratios of these. So that's how you can see blood flow directly. You can see uptake of certain chemicals in different regions by the areas where there are those differentials that are in. So you can see, yeah, was that a question? Yeah.
You mentioned earlier in the class, the previous class, that because the magnetic fields aren't perfectly straight, there's a little bit of
Yeah. So that is another one. No, you're exactly right. So what happens with all of these, I didn't include that one in, although I actually have some papers in the literature on this, that if you look, so here's your tube. It more fits with next time, but it's helpful. It is a good one to use. We're going to consider that the magnetic fields look like this in between, you know, magnets top and bottom and shows and everything else. Reality is they don't look like that. They look like that. Right? And they're arched. So they follow what's called the sum of spherical harmonics. Which are basically terms, you consider this your z-axis, and then the off plane you'll see are going to be your x and y, respectively. And so it's going to have terms that look like z squared and x squared plus y squared. and combinations of those to higher powers. So you have z to the fourth, you'll have z squared times the quantity x, right, so on and so forth. That goes on. So it's made up of these, so you get these curves. In the middle, if you slice, it's pretty straight. The further out you go, the more the bending occurs. In a typical sized MRI machine for a human body volume, it will depend on how strong the field is, as how much bending can occur. If you're in, let's say, less than 5 Tesla, you can get 2.5 millimeters of variation from where it thinks it is to where it actually is. And it's not, it's kind of saddle shaped. Imagine you're cutting through these. So some of them kind of have the hourglass ones, some of them look more like a Pringles potato chip, like what's saddle shaped, things of that sort. So it's not like it's a neat inversion of them. Now, a lot of us did work on what's the mathematics, how can you model it, and so there are calibration techniques you're supposed to do every morning. The cheesy ones do a 2-dimensional one, because you would expect x and y to be the same, so I can do like an XZ and I can apply it circularly to correct it. In reality, the components aren't exactly the same, and the tuning isn't the same, but it's better than it would be if you did nothing. The really good ones for 3D, so slight brag, for probably about 10 years, my group, when I was in California, had the best technique in the world at the time. So, and a lot of the later ones are just based on that same idea we did, which was basically inverting that field, having it measure in precision shapes and invert it. So it is kind of a fun thing, but there is that deviation. Another way that you can handle it, and this is the way a lot of people avoid the calibration issue, if I take an X-ray CT, which is crazy accurate in resource area, and I take an MRI, then I can deformably register the MRI to the X-ray CT. And then I get the best of both worlds. So that's another one that does matter, and that's a good thing to mention. All right, we feel good? You always want to keep in mind what's in there and how do we go. So this is my really overly dense one of how does this work. So we've got, our charged area. That charge, it's spinning. You can see phi on the top right, it was kind of functioning like our axis. A charged body spinning is going to create that magnetic field they're showing. All right? I get a whole bunch of these different ones inside some sample. And if I impose a magnetic field, it will magnetize that sample, and I'll get a net magnetic field out. There will be some variations possible within them, which is what I honestly grabbed this picture off the internet and added a couple little details myself. But this kind of shows it better than the book's picture did. So you can imagine initially all those ones pointing in whatever stupid direction they want. All right? So the net, all these different directions kind of cancel each other out so that there's no really discernible area. If I impose a magnetic field, it's going to cause them to line up. And they're going to line up parallel, i.e. in line with them, or anti-parallel, opposed to them. All right? So it's the anti-parallel is a little higher energy. So why would it ever do that? Yeah, so, but remember, we also have spin up and spin down within them, and there is an energy difference between those quantum states. There are also some slight variations within your field. There's going to be other ones that are sandwiched between two particles. And if two other particles come close enough, right, you get a bunch of ones that are kind of spinned in the direction of the field. They're going to impose an anti-spin on whoever gets kind of sandwiched in the middle of them. So there's always a few that are going to line up anti-parallel. The stronger you make B0, the more it's going to force them to line up, right? Because you've got a stronger field doing the aligning. So if it's weaker, you'll get a bigger spread, right? That essentially, if you summed up all the parallel and subtracted all the anti-parallels, that's going to give you your net field. So the net field will be proportional to what you impose on it, because it depends how well do you get this parallel, anti-parallel combinations. That's really where that difference goes. Stronger B0, more parallel, bigger M. Make sense? Okay, so that's what you're doing. That's the first thing. When we get to the area when you're working it on a body, we're going to take those magnets. There's going to turn out to be a bunch of different magnets inside. This is going to be the big one that imposes that kind of head-to-toe field upon you, right? And then we're going to put a slight wedge to that to cause it to change across your body so we can quantize out, but I don't want to get into that yet. So just imagine right now, this is the big one, head-to-toe in your body. We're about to talk about some of the side ones so we can impose magnetic kicks, so to speak, from the side. You know, these RF pulses. So far, so good? Okay. So right now, if you consider it, right, we've got this, you know, gyromagnetic ratios. Technically, gamma is the standard one, right? But gamma is in radians, and an awful lot of people like dealing with hertz. So just like anything else, you know, we have your frequency and we have your angular frequency. Same exact thing here between gamma and gamma bar, or gamma cross out, I should say. You know, it's just related by 2 pi. And that's because the regular gamma is in radians. I have to take the 2 pi conversion. All right. When we consider our M, the magnitude of that field can be given by the equation I've included. Most of those are constants, but you can see that B0. So again, B0 with the bold is the magnitude and the direction. And we call it B0 again because that's going to be our base head-to-toe one. If I just want the magnitude of this, that's the B0 without the bold. So M0 is directly proportional to B0, which is exactly what we would expect given the alignment of the parallel versus the anti-parallels that are coming in. No shock there, right? If you think about our gamma, whether, you know, slash through or not, right, that's kind of telling you for the particular material, how well does it respond to things. So it's not surprising that one is going to fit in as well with the field. And you see it appear squared. You see Planck's constant also comes in. Planck's constant comes in almost all of these type of equations. That should not, again, surprise us. Let me go to the bottom before dealing with proton densities. You know, 4, we've got K, Boltzmann constant. Again, when you see KT together, okay, that's the thermal relation that we're going on to translate these. So not surprising on that. We see KT together all the time to take temperature into our air. So great, Boltzmann's constant taking our temperature. So we'd imagine as the temperature goes up, the magnetic field, our response is going to go down. It's kind of annealing it in that sense if you think about it. Okay, so that's basically where these ones go. We feel good about how we can calculate. So almost all of the, except for the PB and the B0, are going to be a constant. The gamma or gamma bar is going to be material dependent. PD is also material dependent. It's the proton density. Now, it's not always proton density, but it's almost always proton density. Since in general, you're going to tune the way you are measuring to measure one of these things. The most common one is to measure hydrogen, and hydrogen, as far as we're concerned, is just a proton. Because we don't care about the lepton in orbit, right? The electron is a lepton, and we don't care about that. We care about the composite quark in the nucleus, which is the much bigger response signal for us. Leptons do not interact as strongly with things, so it's not as common to measure anything that's a lepton on there. If, as a side note, are there materials that act like bosons? in general, most matter is associated with fermions, right? But is there any net boson? What are bosons? Maybe quick thing. Fermions are typically associated with matter. Bosons are typically associated with forces. So opposing fields. Is there any matter that functions basically with statistics similar to a boson? That's the even number of quarks. They cancel each other out, right? And because you have a spin up and a spin down, if they come in pairs, right, which is why the even numbers, their spins cancel each other. You can't ever align both of them in the nucleus the same way, because the other neat thing about fermions is they obey the Pauli exclusion principle, which means you can't have two ones in the same spatial area in the exact same quantum state. So it's impossible to align them. So if they come in even pairs, they cancel each other, giving you a net spin of 0, which is basically what a boson is. So they're boson-like. So that's why you notice all the ones we're dealing with are odd. Right? The even ones are the boson-likes. Anyway, we'll tune it for one of these. The by far most common one, because as was mentioned, it's generally your 2/3 water, and water has 2 hydrogens with it. So there's just a crazy amount of protons inside your body. So on all the standard runs, what you're measuring is protons, so PB is your proton density. Technically, it's whatever fermion or composite fermion you're trying to measure. What is its density per volume is what should go into that area. So if I was doing this same thing for fluorine, or whatever, say carbon-13, right, measuring them, then I would obviously in that case have to have technically be a carbon density. You do have a lot of carbon in you. Carbon doesn't respond super huge though. So you could actually, could I use this to figure out any radioactive issues on here?
If the type of I'm trying to find is odd,
Yeah, so think about carbon-13, carbon-14. Carbon-14 not going to show up, so you can actually, in that sense, if you have a general way to measure the overall carbon, you can get a very accurate measure of the carbon-13, and therefore figure out the differential between them. Anyway, just a side note. There's a lot of fun alternate uses people have not thought of about these, right? Anything you do, there's weird ways of looking at it that let you exploit something else. So what do you want to measure off of? All right. If you consider for here, right, we have M now, that's our, in essence, the magnetization vector for it. We have our angular momentum, and we have for our particles, they are again related by that lovely little gamma, in this case without the strike through. So it's, the non-2 pi version, but again, who cares? When we take this and we take the derivative, right, of J, it's caused by the cross product, right? This is, I've got my M and my imposed B field that's going on. The cross of those is going to actually give you what's going to change your angular momentum. So this is the same as if you had a spinning top, so you hit it with a force. It's the cross product that determines. That's why you can, anybody ever see the bicycle wheel suspended from the ceiling? Experiments, some yes, some no. Yeah, you just take like a rope, right? And with a little loop on the end, you start a bicycle wheel spinning, you put one side of the bicycle wheel spoke in the loop, and it'll start rotating, it won't fall, right? It'll just sit there perfectly circling in an orbit on that string, with the string staying straight over it just as it goes around, because it's a torque. Right? The downward force and the spin axis of the tire causes, right? You can do your lovely little right-hand rule and you will get the spin of it. That's the same thing we're doing here. All right, so the change in the angular momentum is going to be proportional to the cross product of the imposed B field, kind of like your gravity, and right? Your magnetization vector, which is in the direction of the next spin of your atoms. So that's your bike tires circling on the ceiling. I don't know if they ever showed that one in physics, but it's one of those kind of, it's like you conceptually know it, but then when you watch it happen, it seems almost mystical how this thing keeps going, right up until it runs down, and then it just, you know, if you haven't seen it, it's worth watching. All we have to do then is multiply by the gamma, though, and gamma and the J gives me M. So woohoo! Now I've got a differential one like M, which is what I really care about. Away we go. So if we took this same thing, we could decompose it. Imagine I had a fixed B field, which is what we've got head to toe, and that there was some difference between the two of them. So, here's my M, but, if you imagine the B field is kind of aligned with Z, so I did something to kick it out. Right now you're going to get precession, and, how much you have kicked it out, and then it's going to rotate around, right? So the alpha is the precession angle that's going on, and then we basically have, here's your rotational speed, which is called the Lamour frequency. That's this new zero here, which again, although the gamma shows in our B0, the stronger you've got B0, the faster it's going to rotate around here or spin. And that's right, the value. So obviously the X, ooh, I was supposed to change that. That's supposed to be Y. So my bad. Here, I'll try to fix that. I just did the first one, then copied it. And I fixed the sign and then forgot to change the Y. Copy and paste error. Anyway, you can see the effect of that with this important Lamour frequency. And these are the equations basically derived from here that tells us exactly what we're going to get behavior-wise inside this, how it's going to, that axis is going to precess. And that's what we're actually going to measure. We're going to line it up, and then we're going to provide a series of kind of colloquial, we call them kicks or impulses, if you want to think of it. We're going to hit the atom to knock it off. Right? It's going to be spinning nice and aligned. We'll hit it. When you hit it, you ever take a spinning top and hit it? And it'll kind of wobble a bit. But if it's got a lot of spin momentum, it'll damp out and it'll get nice and straight again. Right? That's what we're going to do. And we're going to see how long does it take to fix itself. And we're going to take a look when we're hitting a whole box full of them. Imagine I had a bunch of spinning tops inside a box, and I just shook the box, right? You'd imagine they'd all get different phase impulses, right? When I first kick the box, they're probably all in the same, right? Because they all got hit the same. But then over time, there's going to be some little variances. They'll have a little bit different mass, so they'll have a little bit different inertia, they'll have a little bit different speeds, things of that sort. So they'll start, initially they'll get kicked the same way, and then they'll start fuzzing out based on they'll have a different phase of their spin, right? That phase will give us a response we can read, so we can watch how it dephases. That will also give us some information about the materials. Different materials will dephase at different speeds. So our whole trick is going to be this idea. Align everything up and kick it and see what it does. And how it responds will tell you what the material was. That's why it's so good at measuring soft tissues. Soft tissues, lots of protons, and they have a different way, right? The environment is going to affect this rotational velocity. Right? Lamour frequency. Make sense? That's really at its gut core the concept that's going on here. So let's talk about how we can do this kind of kick and dephase. So again, remember, it was initially up pointing in the direction of Z. We're going to kick it down to M, right? And we're going to kick it by this B1. So remember, B0 is in the direction of Z. That's the overall imposed field. Because we want to look, we want a static field that's going to kind of correct it naturally to bring them back in line. So B1 is our kick to the side, right? It's 90 degrees off. And how you kick it will determine how far it goes. What we do for these is we measure, right? We actually can calculate these. how long do you have to kick it 90 degrees or 180, right? So, and we're gonna have different pulses, and you'll see, we'll just label 90, 180, whatever, which is how much we wanna kick them. How far do we want to de-spin them to watch those come down? And those can be completely calculated by the materials. For time's sake, I don't think it's particularly profound. It's really stick it in the equation and chug. So to me, I didn't really include a slide on that because I thought it was boring, honestly. You know, the interesting part is I kick it, you can see that field, it'll spin out technically. So the pulse is not going to be an instant kick. We're going to actually have some patterned pulse to it, and it'll spin me out, and then I'll start spinning back on my own. That makes sense? And that's what that was kind of doing. And it will then kind of spin backwards as it goes back in line with it. So as a picture, kind of we do this FGH here. It's nice and aligned. I give an RF pulse. So we call that the RF coil that's kicking, doing the B1. Right? It's going to do the kick to the side, and this is the absorbed and everything that came from the radar experience, hence the name RF coil. It will do it, and then it'll give you a response back to the RF coil. So much like ultrasound, that RF coil is going to be our signal source for kicking them, and then our measurements back, just like the transducer was, and we're going to measure those patterns with it. Does the basic idea make sense? Right? Kick it out of phase with an RF pulse, it'll go back into phase, giving you an RF pulse back, right? And how that RF pulse looks and the time constant and everything else will depend on the material, right? Because the chemistry around it's going to affect it. Yeah.
I have a question. So on the FGH diagram there,
Yeah.
it seems like, and I don't actually know what happens here, but it seems like it's saying after the M vector realigns with Z, then it produces the
No, so this is an oversimplified one, but I like the fact that it included it. What's going to happen is I'm going to kick it, and it will take time to get down.
And so while it's
Right.
going back,
Now, as it's coming back, you're going to get that.
okay, great.
You know, and it's actually not super strong. So we're going to add in some extra pulses. We'll do some 180 pulses that will give us a stronger signal, right? Because once it's down, if I do a 180 pulse, I'll show you why. It actually gives you a stronger one, and it has to do with the dephasing. So remember when I said you kind of kick the box and they all end up going one way? And some of them are spinning a little faster and some a little slower. So they kind of, that phase pulse goes away, right? But so that means the faster ones are dephasing quicker than the slower ones. What would happen if I did a 180? I inverted the box.
They'd all be down.
Yeah, so now the faster ones, which are more out of phase, are going to be coming back into phase a little bit quicker, which means I'll get an echo. We'll talk about this in a sec, right? So there are ways we can strengthen this response by giving these 180 kicks, which create echo pulses in line with it, and it'll help us. But this is the basic idea. Imagine I took this and did just knock it a little bit. I knocked it all the way to a 90. That's our 90 degree or pi over 2 tip, right? Here's that dephasing I was talking about. If you assume they were all the same, they would naturally dephase at one rate, right? So partially, a little bit more time, they dephase more. Eventually, they completely dephase. And even if it's not perfectly realigned here, you can know once it's dephased, you can't measure it anymore. Does that make sense? Right? If they were all perfect duplicates of each other, right, they would do so at kind of a reasonable speed for this. Actually, I'll get to this in a sec. I want to give you one thing from here. Right? That decay speed, if everything was perfect, is called T2 decay. That's everything is perfect, they're all identical, so there's no fast or slow ones. So that's kind of expected behavior, perfect material. Life isn't like that. So in reality, you've got some faster, some slower, some difference. That's what's T2 star. So I just want to jump to here, just so when we talk about T2 or T2 star, I just want in your head what those things mean. Okay. So let's take a look at this a little bit more. So we have our RF coil on the side, right? Gives us our excitation, right? There's a static field going from the bottom to the top, right? And when that goes in, right, we're going to get a net field coming back out. So we get a proton relaxation signal that's talking about, right? We take that signal, Fourier transform, it gives us our spot, right? You know, so, and then here you can kind of get a ramping one in mind. This is a little bit fancier, we'll talk about this more, but I can get one so that I can impose a changing field across you, right? That don't have to make it constant all the way. What that's going to allow me to do is actually resolve the spatial dimensions. So just when we do these, I can actually impose a little bit of an angulation on it. We're going to do that same thing head to toe. We do the same thing left to right. And now you can resolve the different positions because the net value of the fields are different for B0 and B1 in different locations. Right, so you can actually, this is how you can encode spatial information, is by imposing those fields. Otherwise, this is just the same as the other one, it's just a little fancier picture. There's an actual coil instead of just the letters RF, right? And it tells you I do a Fourier transform of that measured signal to get basically the location. We call this the decaying signal that comes, we get feedback, we call it FID, right? That's the free induction decay, that's the dephasing, whatever you want to think of it. You'll measure it. There's the actual induction decay and there's the envelope. That envelope gives us our times, the T2 and T2 star, respectively. You will not directly measure T2. Because again, reality doesn't, well, I should be a little careful of that. So in the short term, you will not measure T2. So when you're measuring this FID, you actually don't get a constant thing. You'll get the first part of the curve is really heavily governed by T2 star. As T2 star gets really, really small further out, it essentially goes away. The material itself, on average, is behaving like they're all the same, right? So there is still a little bit of that T2 field that still exists. So if you're way out, this part of the field is actually going to be governed by T2. Right? So there is a sense, so on the echoes, when you go farther out, you can force the echo by its spacing to be more T2 sized by when you're doing the measurements on them. But in general, when people talk about the FID decay, they're really concerned with this part of the curve, which is the easy measurable, and that is T2 star. I don't remember if the book mentions this difference or not, but it is an important area because there are ways we can get to them. Anyway. Yeah.
So, the book mentioned that the RF excitation that is here is not actually like an EM wave. So that's kind of a misnomer. But how do you get something at an RF frequency that's an oscillating magnetic field without making an EM wave?
Yeah, so there is a coil, right, that's going on, and you are going to impose it. That's why they often will call it kind of, it's small and it's encoded across. So it is EM, but this is partial where it gets into the RF area. That in this sense, it's kind of, in my sense, an unnecessary distinction they're making, but it really, they're getting at the fact that it's kind of more like those RF pulses in some sense, right? But it's reasonable enough, unless you're actually building the RF coils, not to understand. And this is where the noise part can kind of creep in because it is actually very low. And the magnetic field, if you were imposing a regular one for any duration, it would be strong, right? Because the magnetic field is where pretty much all of your energy is, right? And this is a very weak one. And that's the only area where I really see the necessary to make that distinction. All right, so let's talk a little bit about these when they go in. All right, so there's two different decays we've talked about, T2, T2 star. And that's really in the plane, the XY plane. And it has to do, it's sometimes called the spin-spin decay because it's the X and Y directions, the spin dephasing. There's also the going out of that plane towards the Z axis to where it's aligned up and it's no longer precessing. We usually call things aligned up with that Z axis the lattice. So when we do that, it's also called the longitudinal recovery to it, but it's basically the time it takes for it to get aligned back up with the Z axis. That is called sometimes the spin lattice. I don't think I include that here. I don't remember if the book mentions it too. But if you talk to practitioners in the field, the majority of them call these spin-spin and spin lattice. Right? And the reason why they give them those names, spin-spin because you're dealing with the XY plane, and spin lattice because you're dealing with this transverse one in the longitudinal to Z. It's how that damps out. How do you get out of that? So it's from the spinning part to align with the entire lattice. That's the longitudinal recovery. And when I stole these out of their books, I noticed they didn't really give the time thing of this. This is a general guideline. It is not true in absolute all the time. It is generally true that T2 star is less than T2. That's really, really common. There are some rare exceptions, but you basically, there you go, right? In general, T1 is typically bigger than 5 times T2, but it's usually less than 10 times T2. There are exceptions. There are actually some cases where T1 is less than T2, right, where it's really, really short, right? But for the vast majority of tissues, it's in this range. This separation, T1, because it's longer, is going to be really hard to measure. Right? Naturally, you're going to get T2 or truly T2 star. We're going to have to do some fancy stuff here. But because this one decays slower, right? You can see the T1 following that same initial slope curve, right? It's the exponential. And in general, this one's going to last so much longer, it'll have more energy. Different ones will have different rates of these. So we're going to create, when we get to these, we'll let them dephase to the point where T2 is all gone and T1's the only thing that's happening, where it'll still be coming back in. But in essence, it's not, you don't really have any coherent amount of T2 appearing because they're dephased, right? But you still, they haven't aligned back up. We'll take advantage of that because if it was already angled when we kick it, right, what it's going to do is it'll kick that off angle down into the plane. And so the magnitude of your phase is going to be dependent on what that angle is. Okay. So that's how we're able to measure that one. So you'll see we'll kick it, we'll give it a long enough period of time that it'll be able, it'll be dephased for the T2 stuff. We'll kick it back into the plane. And so now the angle, alpha, is the only thing that's going to give us now a measurement size. And so ones that decay faster here will have less of a signal than ones that were decayed less. And so now, in essence, the magnitude of the signal of the new, now we can measure it as T2, because the magnitude of T2 will be proportional to T1, because we use that tipping point to to be our measured angle. I'll show you an example on the next slide. But I just want you to look at these. The fact that they're different allows us to take advantage and do the measurement. So these graphs are a lot more important than they look, right? You just look at it, well, exponential decay, right? But it's more than that. Okay, let's say I wanted to get kind of my standard type of a measure. You can see here, we show below, and this is kind of graphically what's happening. I come up and I initially have my little pulse that gives me 90. That's that first one, the pi over 2 tip. Boom, it's there. Things start dephasing, right? As it's dephasing, you're getting this FID, right? The free induction. All right, so that's your FID here. There's the envelope that's coming down. It damps off. It's not fully, this means it's dephased at that point. If I wait a little bit after that, so I'm further past it, right, I can now hit this with 180. So, right, it's been dephasing, dephasing, it dephases to a certain point. I do a 180 inversion. And again, the ones further out, right, that had dephased more are dephasing faster. That's not an accident. It's actually proportional to magnetic field variations, material variations, things of this sort that cause them to just be there faster in dephasing than the other ones are. So when you do the 180 inversion, the fast ones are now coming back, right? You flipped it, so instead of going out, they're coming back in. So you've got the faster ones further out and the slower ones in. So now it's a race to the finish, right? And that's what you get with the echo. So you put this exactly halfway. And then the echo, now the faster ones are catching back up with the slower ones, and you get an echo. And then you get another FID. It's lower than this one is because you always lose something, right? But it's stronger than you would have had otherwise, right? And so this now gives me a way that I can kind of measure, and the faster ones ran away and then ran back, right? So it's kind of like, imagine you were back in high school or something, you're in gym class, and they take the track kids and they make them run the basketball players and make them run the farthest, you know, and you kind of progressively match it down based on physicality so that the slowest kids have the shortest distance to run before they have to turn around. So it's a real race at the end, right? That's actually what we're doing, right? We let the athletes run out a bit, and then we just, you know, they kind of naturally separate themselves, and we say, turn around and run back. First to the finish wins, right? Well, because they spread out based on their speed, they're not going to come back together based on their speed. But they're really far out. The longer I let it run, the more they've dephased. All right, so remember what I was saying, if I want to aim this, if I do this, the 180 pulse here, it's heavily governed by T2 star. If I wait till I'm further out, it's decayed, it's weaker, but it's more governed by T2 further out when I do the pulse come back. And I can get more T2 type weighting. Because it really does have kind of two time scales in that graph, as long as you ignore the middle part where it's too much of both. Does that make sense? So this is the basic procedure if I want to measure them, and we get these echoes. And the echo is the strongest you can get. And then it's just, we set this TE over 2 to depend on what we're trying to measure. Right? And it's a 90 and a 180, right? Right. Turn around and run back. Measure the results. Make sense? So if you kind of put it in simple terms like that, I think it kind of helps.
So I think I understand the general concept. I just have a few kind of
Sure.
questions. So,
And we'll go through in gory detail
okay.
when we do next time. This is the basic idea. We're going to talk about the equipment, and we'll get into a lot more. I'm trying to hand wave it here because I want you to have a framework in your head of how it works, and then we'll go through more detail.
Okay. So yeah, some of my questions were going to be on how can we do that, but I guess we'll save that.
We'll do that. That's next class.
Okay, great.
Because this is chapter 12. That one's on 13,
Right.
and I'm trying to keep you in pace with the reading.
Okay, makes sense. So I have a question. So in the very bottom right corner where we have first race and then we flip it and everybody writes back. We have the FID curve, which is the envelope, and then the echo envelope. which or both corresponds to these graphs over here, or is that on the other way?
This curve that you see down here
That seems like
is related to the T2.
Okay, great.
Right? You're not measuring this now. That's going to be on the next slide.
Okay.
Right? So,
Okay.
and technically, it's actually an overlap. That's what I was trying to tell you there. The upper part of this is really much more T2 star. And as you get way far out, it's much more of a T2 thing, right? Because they've already spread and, right, the phases, they're all mixed. But there'll be some variations within them, and that variations within them are going to have been spread out now. It's like, imagine again, let me do my running analogy, right? Imagine you've got a track, you're running around the football field or whatever. Again, you've got the track team takes off, right, and they're way ahead. And, you know, you've got regular athletes, and eventually you get down to the people who just don't exercise, right? And they're spread. Now, what happens if you're doing multiple laps? Well, eventually the track team, basketball team, whoever is passing the slower people, right? It's dephased now, right? You can't tell by the phase what's the angle within the track as to how fast you are. But is there still some variations within that group? You know, even though they're overlapped, so you don't have big chunk areas, is there still a little bit of a wave passing through there? Yes, but now you've got the fast people have even started to spread out amongst each other, and the slower people are spreading out, and they're all mixed together. So there's going to be these kind of regional pulse areas, and that's going to be actually proportional to the T2 decay, because now the properties have kind of evened out and everybody's spread. So it's no longer how fast you are per se that's mattering. Now it's overall materials as to how much energy you have left. But it's an averaged across everybody with all their different speed things. So it really is much more the assumptions of T2. Everybody's kind of equal in a region. You've got fast people and slow people averaging together in all the regions. But the decay is still there, right? So there's still some energy left, and that's what's happening at the tail here.
Okay. And so the echo is just going to be that same thing, but transposed and a little
Yes, coming through, and then it'll start. Once you get to that, and you tell them to reverse directions, you know, let's say you did it fairly quickly and turned around, you know, it's gonna chaotically, and if you kept telling them to keep running, it wouldn't take too long before the fast people start spreading out again. You're not gonna get all the way up to the pulse, right? Same thing said, no matter how far you do, it's gonna get to the point where the bulk of them are crossing the line. And then it's gonna start dephasing again.
Okay. So I guess one last question. So this dephasing that we're talking about, that's phase in the XY plane, is that right? So on what time scale does the Z recovery happen? Or I know you said it's about
That's-
5. Yeah.
For
So,
most materials in your body, it's between 5 and 10 times the size.
okay, so would those, the TE over 2 TE, would those be about 1 T2 and 2 T2, or?
So in general, if I'm trying to measure the T2 stuff, right, I'm gonna want this to be way below this.
Okay.
Like, you know, somewhere on the order, say 1 or 2. Right? When you start getting to 3 or more, most of that's gone. And so you're really starting to get into this zone where your T1 is no longer ignorable. Right? So you usually want it in a very short time period on those. Right? And so by picking the time frames relative to each other, it's actually much more of a pain in the rear if the material has more similar T2 and T1 times, because it's going to be hard to get that separation to be able to ignore one versus the other. That's great questions. Okay. Let me just show you kind of what you get from these, and then we'll show you how to do the final one. We're almost out of time, but I kind of want to do it on here. There's different ways. Like I could weight it just on the proton density. I just try to do all my signals to measure out and figure out how many protons are here. Right? This gives you some idea for a brain, right? White matter about 0.61, you know, would be about the values. Gray matter about 0.69. The fluid around your brain about 1.0. Notice when I go to T2 weighting, just the in phase, the spins, right? The weighting of these, and again, this is in milliseconds for where they're going, right? 67, 77, that's what I'm measuring when that pulse is gonna come back together, right? The white matter versus the gray matter, when those materials are gonna spike, versus the fluid. That's why I get pretty strong images in them. But notice it is different. I'm actually seeing different things because the ratios of these are not all the same. The bigger the ratio difference is, the stronger it shows up in contrast. So there are some pretty significance. If you notice when I go to T1 time, the difference between these two, like drop the zeros off for a second, and you'll notice 76, 77, pretty darn close. So if you look down, the difference between gray and white matter is different. You'll see better brain contrast. And if you look inside here, most of the brain is pretty similar there, but you do, I mean, you do get some contrast, but you get more contrast here in the tissue types. But if you look at this from 76 to 265, and dropping the zeros, as opposed to 77 to 280, the difference between physical matter and the fluid is more noticeable in T2. Right? So what are you trying to find? Right? I mean, if you're trying to find a hemorrhage in the brain, well, this is going to make more sense. If I'm trying to distinguish some certain types of tissues, this one's going to make more sense. If I've got a particular type of tissue that has a drastically different amount of protons in it, then proton related is going to give me a good separator for them. So you can see the images of the different weightings are significant. The top part of this, I just give you for T1 and T2, bright versus dark areas. So, T1 weighting, right, white matter, fat, slow moving blood, things of that sort, right? As opposed to on the T2 weight, you're getting more gray matter, high water content things, right? Tend to respond better to it, right? Whereas the dark ones on the T1 weight, right, you get the gray matter, bone, air, water content, things of that sort. Inflammation, those all show up nicely. White matter, bone, air, low fat. Notice it's different stuff, right? And so that just kind of tells you can look at those and tell, and it will tell you different material areas. So depending on what you're trying to look for and separate out, will depend on which one of the weightings you want. How well does it do in resolving my material differences? All right. This is in essence what we did for the first one, right? Kick it, cause the echo, measure the echo. All right? There's a certain recovery time, and then I can do the whole damn thing again. All right? The recovery time, you have to let it basically get to the point where T1 is gone, right? Because if T1's not gone, you've got a problem. If I'm doing an inversion recovery, this is what you do if you're trying to get the T1 weights. So it doesn't actually mention it here, but what I'm going to do is I'm going to kick it a whole bunch of times leading up. Right? And I just keep kicking it. It helps to dephase it, right? While keeping, it not lined up with the Z, because every time you kick it, you kind of knock the phases around. So if I kick it a bunch of times, you can imagine it's pretty dephased, but T1 is really pretty strong still, right? And then once I'm in that situation, I can give the 180 pulse. This is going to cause it to start pulling back together, right? Now that's on. And at a certain point, this is now basically all the phases are gone. And I'll give it, it's just how far you are from the Z-axis. The axis, here you go. Give the 90 pulse. And again, the angle, when it goes, how far you are from there is going to tell how strong a signal you're going to get in the XY plane. So ones that have decayed more will have less of a signal than ones that have decayed less. And so when I do this kit, it turned all of that Z differential into an XY differential. Because the starting position in your XY has now been made proportional to how much of your angle from the Z was left to go. And then, since that is now a measure of T1, right, because T1 weighted how strong it is, I give it a little time and I do the same stupid echo response, right? I'm gonna again be measuring XY, but the XY strength is proportional to T1 now. So I can measure T1.
So is it fair to say that we don't really have a way to directly measure T1, we just use fancy?
We have to do this little trick. And we wait till basically the phase is gone, but it hasn't lined back up. You know, and our initial 90-degree kick was assuming it was in line when we kicked it. Then there was no variation. But now they're all kind of angle difference. So how far you are will now determine how spread it is. And that's really the trick. By noticing that, we go, okay, now I can do the thing I know how to measure. And it looks, at that point, exactly the same. Because it is, right? So it was do a bunch of stuff to get rid of all the phase areas, but leaving it still not converged to Z, and then bring it back in and measure it like you normally would. And your bigger variation will be the T1 differential now. That's basically the trick. So I believe that is our time. Yeah, this is just a picture of it. All this picture in the book is trying to say is someone's had a long T1, so they haven't changed very much in their angle. Some of them decay really fast, very much for that. That's all they're trying to say. And then when you kick it, how far it is will determine what the axis is. Right? The more it is lined up, the more it looks like a regular kick. Awesome. Yep, that was it. So, have a lovely day. Oh no, where did my recorder go? Well, hopefully that recorded and it didn't just die on us.